If you believe humans are the masters of nature and our intellect is limitless, you are greatly mistaken. The speed of light in a vacuum is just one of many insurmountable barriers for human beings. The highest speed ever achieved by humans, approximately 40,000 kilometers per hour, was reached by the Apollo 10 astronauts. While this feat caused a sensation a century ago, modern humanity has far more ambitious goals. The target is now 1 billion kilometers per hour, the speed of light, a figure currently confined to science fiction and NASA simulations. However, significant challenges await scientific enthusiasts on this arduous path. Problem number 1. Speed. Current speeds achievable by humanity would take over 2 million years to reach even relatively close stars like Aldebaran for the Voyager probe, which recently exited the solar system. Reaching Proxima Centauri, the closest star to our solar system, would be even more challenging. With speeds achievable with current technology, a journey to Proxima Centauri would take thousands of generations. For comparison, an ion thruster, under ideal conditions, can reach speeds up to 56,000 kilometers per hour. At that speed, a journey to Proxima Centauri would take approximately 81,000 Earth years, representing around 2,700 generations. This renders such a voyage practically impossible. Even utilizing gravitational maneuvers, allowing for maximum speeds of approximately 240,000 kilometers per hour, the trip to Proxima Centauri would still take roughly 19,000 years. Even a hypothetical spacecraft traveling at the speed of light would take tens of thousands of years to traverse the Milky Way galaxy, which is 100,000 light-years in diameter. A trip to Andromeda, at 2.5 million light-years away, becomes incomprehensibly long, further complicated by the fact that the light we see from Andromeda is millions of years old. This means that by the time we arrived, Andromeda might be a fundamentally different galaxy or even non-existent. Problem number 2. Building the spacecraft. Constructing a spacecraft that can even approach the speed of light is currently inconceivable. We lack the necessary fuel and materials. The immense G-forces experienced during deep space travel at high speeds require incredibly strong materials of unrealistic scale and revolutionary new propulsion systems. For instance, a spacecraft utilizing thermonuclear fusion would need to be the size of a small planet, weigh as much as an elephant, and be completely filled with dangerous fuel. Assembling such a structure in orbit, let alone on Earth's surface, is impossible. To propel a smaller spacecraft to speeds approaching light speed would require more energy than all of Earth's power sources produce in a month. Scientists have considered antimatter propulsion, which could theoretically propel a spacecraft to 70% the speed of light. However, this presents even more significant problems. The annihilation of matter and antimatter produces an unimaginable amount of radiation, making survival aboard such a spacecraft impossible. Furthermore, storing antimatter is extremely dangerous. Even the slightest contact would cause a catastrophic explosion. Creating antimatter is also incredibly expensive and short-lived. A milligram of positrons costs $25 million and lasts about 20 minutes. Desperate scientists even contemplate creating artificial biospheres within asteroids that could journey to nearby stars over the course of many generations. However, there is a risk that over thousands of years, humanity could forget the purpose of the voyage, losing its original identity and the journey itself becoming just another legend. Problem number 3. The hostile nature of space. The vacuum of space is far from empty. At speeds approaching light speed, even particles like hydrogen atoms and cosmic dust would become lethal threats. At 20% the speed of light, these particles would bombard the spacecraft's hull, causing significant damage. At light speed, the impact would destroy the vessel and its crew. The impact force would be comparable to a beam of protons accelerated in the Large Hadron Collider. No known material could withstand such attacks. While a hypothetical protective shield could be designed to protect against such bombardment and lethal radiation doses, it would have to be hundreds of meters thick and weigh hundreds of tons. The challenges are immense, making voyages to distant stars at light speed seem impossible, even in the distant future.